Hello, in the previous clip we looked at how to execute 2 degree of freedom control design in order to achieve robustness against variation of the plant's pole, and that design procedure followed along the same lines as the design procedure that we had discussed 2 clips back, where we had discussed the design of a robust control system that is intended to achieve the specified amount of robustness to variation in the plant's gain. The only difference in the previous clip was the kind of trajectory along which the closed loop pole varies when the plant's pole location changes. This trajectory was different from the trajectory that the closed loop pole took when the plant's gain changed. So the only thing that we had to do afresh was to derive the trajectory along which the closed loop pole changes due to variation in the plant's pole. Subsequent to that, we could adopt the same steps that we had adopted earlier in order to determine the location of the controller zeros and poles, and then complete the design of the feedback controller and subsequently also the pre-filter. Now the design strategy that we have been discussing over the last 2 clips is more general than just being able to handle uncertainties associated with just the gain or just the pole location of a plant. In fact, it can handle simultaneous uncertainties associated with both the gain as well as the pole position, and indeed uncertainties associated not just with one pole but also with other poles of the plant. So what we shall see in today's clip is to how to undertake design when you have uncertainties in multiple parameters in your plant and achieve a robust control system whose dominant dynamics does not change by more than a specified amount when the plant's uncertain parameters vary within the bounds that have been specified to them. So let us take a look at the problem that we would be handling today that has been stated on this slide. We are going to stick to the same plant that we have been discussing over the last several lectures. The plant is P of S is equal to K by S times S plus P times S plus 2. In this case, the gain of the plant K is assumed to be uncertain, unlike in the previous clip where we assumed K to be equal to 1. Here its nominal value is equal to 1, but its actual value could be anywhere between 0.3 and 3. So the gain of the plant can vary by an order of magnitude. So there is uncertainty associated with the gain of the plant, and this reminds us of the example that we considered 2 clips back, where we had considered only uncertainty in the gain of the plant, and this was precisely the extent of uncertainty that was considered in that example. Now in addition to uncertainty in the gain of the plant, we also have uncertainty in its pole location. So the nominal location of the pole P is equal to 1, in other words it is situated at S is equal to minus 1, but the pole could be located anywhere between S is equal to 0 and S is equal to minus 2. In other words, the variable P in this equation can assume values anywhere between 0 and 2. Now in this example we have a plant whose gain K and whose pole location P can independently vary between the limits that have been specified here. They have certain nominal values. In this case, the nominal values of the gain K and the pole location are both equal to 1, and they have a certain variation, a range of variation in the values about the nominal value. The dominant closed loop poles of the control system that we are about to design once again is required to be at minus 1.5 plus minus 2j. So this is exactly the same specification that we have borrowed from the previous 2 examples that we considered. And the third specification is that the variation in the closed loop pole, which would necessarily happen when the plant's model changes either due to uncertainty in the gain or due to uncertainty in the pole location, that should be within 0.04 units. And this specification is identical to the one that we had considered in the previous lecture when we had uncertainty only in the pole position. So once again I want to remind you that such a set of specifications cannot be realized with a 1 degree of freedom control system, because the control system can position the closed loop poles nominally at the location where we desire it to be, namely minus 1.5 plus minus 2j, but it cannot guarantee that the variation in the closed loop pole due to uncertainties associated with the plant are going to be within the specified limit of 0.04 units. Hence, we need a 2 degree of freedom control architecture where we have a pre-filter as well as a feedback controller. As far as the design of the feedback controller and the pre-filter are concerned, we have looked at some standard guidelines that are associated with their design. In particular, we know that our feedback controller needs to have a pair of zeros that are located very close to the pair of dominant closed loop poles, which we have in this case called PCL0. These are essentially the poles minus 1.5 plus 2j and minus 1.5 minus 2j. So, we have to place the two zeros very close to these poles, and these zeros have the effect of pinning these closed loop poles and arresting the variation of the closed loop pole due to the changes in the plant's parameters. But because we have two zeros of the controller needs to also have two poles. So, we have to choose to place the poles at some distance, and we assume that they are placed quite some distance away from the origin. And the design steps essentially have been outlined here. Now that we have the structure for the feedback controller, namely that it has two zeros, each of them are placed close to the location where we want our dominant dynamics to lie and to not vary too much, and then we have two poles placed farther away. So, the first step is to locate the distance of this zero from the point PCL0, from the point where we want the nominal dominant poles to lie, namely minus 1.5 plus 2j and minus 1.5 minus 2j. So, this is the first step. The second step is to determine the orientation of the zero with respect to this point. The third step is to determine the positions of the two controller poles that we have placed in the interest of causality in the realization of the controller. And here, if we assume that these two poles are coincident, then we have to determine the location of either one of these two poles, and we discussed in the first clip that this location is determined by stability considerations, because these two poles become responsible for other branches of the root locus which could potentially destabilize our control system when the plant's parameters change. After determining the position of these far away poles of the controller, the next step is to complete the feedback controller design, and that is by determining the gain of the feedback controller. So, if you know the structure of the controller, the gain of the controller can be determined in a very straightforward manner by using the equation that has been given at the bottom here. K is equal to minus 1 by Cp, where this transfer function C and transfer function P are both evaluated at the point PCL0, the nominal position of the closed loop pole. The last step is to determine the structure of the pre-filter, because the previous 4 steps were devoted exclusively to determining the structure of the feedback controller. With the fourth step, we would have the gain of the controller as well as its pole locations, pole and zero positions. So, the final step is to determine the structure of the pre-filter, and as we have discussed in the past, the primary purpose of the pre-filter is to get it to cancel the zeros of the feedback controller and thereby get the dominant dynamics of the overall transfer function that relates the output to the reference to be determined by the points PCL0 and PCL0 bar, in other words minus 1.5 plus minus 2j. So, that cancellation is done by choosing a pre-filter that has the structure that has been shown here. F is equal to ZZ bar by S plus Z times S plus Z bar. The numerator of the pre-filter has been chosen to be equal to ZZ bar because we want the pre-filter to have unity DC gain. So, if we revisit the 5 steps that we have in the design, just as we discussed in the previous clip, the steps 2 to 5 are all very similar in their approach to the steps that one needed to adopt in the first clip, where we had to worry about, where we undertook the design to determine the orientation of the zero and the position of the far away poles of the controller, and subsequently the gain of the feedback controller as well as the pre-filter structure. So, the steps, the procedure is going to be no different from what was adopted earlier in the first clip, and the same procedure was also borrowed in the second clip, and in this clip as well we shall do the same thing. We shall assume that these steps are things that we can routinely undertake once we are able to determine the position or the distance where this 0 z has to be located with respect to the point PCL0. So, it is the first step alone that is unique to the problem that we have posed for ourselves, where we have simultaneous uncertainties in two parameters, namely the gain of the plant as well as its pole position. So, in this clip therefore, we would focus only on the first part of the design, and we shall not discuss the other steps in great detail. We shall simply borrow the procedure from the previous clips and execute the design without describing in detail what is done in each of these cases. So, let us therefore get down to determining the distance of the 0, namely the distance x from the point PCL naught, in order to prevent the variation of the closed loop pole PCL from being more than 0.04 units when the plant's gain and its pole location changes. In order to undertake the first step in the design, we shall look at the effect of each of these uncertainties separately. So, we shall look at the effect of change of gain of the plant and subsequently look at the change of the pole location of the plant. So, in order to undertake that, I have drawn here the complex plane, where in the first graph I have located the points P1, P2, P3, which are the nominal positions of the plant poles, along with the pole locations P4 and P5 of the controller, and I have located the point Z in the upper quadrant of the complex plane. There is going to be a point Z bar, but that has not been shown here for the sake of convenience, and the point PCL naught, where we want the nominal closed loop pole to be located, has also been indicated. So, the second graph here shows the exact same thing as the first graph, with the exception that in the second case we assume that the pole location P2 can vary. So, nominally it is located at the point P2 naught, which is indicated by this blue cross here, but that is just its nominal position. The actual position of P2 can be anywhere between P1 and P3, because we assume in our specification that our plant pole can be anywhere between s is equal to 0 and s is equal to -2. So, if we return to the first graph and we zoom into the area near the point Z and the point PCL naught, I shall draw it in a magnified manner here. So, I shall indicate the point PCL naught here, and I shall indicate the point Z there. In the first case, we assume that we have only uncertainty associated with the gain of the plant. Now, if we have uncertainty associated with the gain of the plant, and the plant's gain can increase by a factor of 3, from its nominal value of 1 it can go up to a value of 3, or it can reduce to 30% of its initial value, then 2 clips back we learnt that the closed loop pole will vary along a straight line that connects the point PCL naught to Z. In particular, we learnt that when the gain increases by a factor of 3, the point will move to the location PCL max, which is going to be 1/3 of the distance from the point Z as the point PCL naught is. Likewise, we also discovered that when the gain drops by a factor of 3, the point PCL will move along the same line in the other direction to the point PCL min, which is 3 times farther away, 3.33 times farther away from the point Z as the point PCL naught is. So, if the distance from the point PCL naught to the point Z, if you were to call that distance to be x, then we learnt 2 clips back that when the gain increases by a factor of 3, the closed loop pole comes to the point PCL max, which is at a distance of x by 3, and when the gain drops to 30% of its nominal value, the closed loop pole moves to the point PCL min, which is 3.33 times farther away from the point Z as the point PCL naught is. So, the trajectory of the closed loop pole is going to be a straight line in the complex plane given by this red line here. So, this is the line along which the closed loop pole would vary when the plant's gain alone were to change. Now, if we come to the second case, where you have uncertainty associated with the plant's pole location, in this case let us for a minute assume that there is no uncertainty associated with the gain. Let us assume for a minute therefore that we have uncertainty only in the location of the pole of the plant. Now in the previous clip we looked at how the closed loop pole position changes when the plant's pole location changes. In particular, we discovered that if the plant pole position P2 changes between the points P1 and P3, then the closed loop pole PCL changes between the points PCL min and PCL max in such a manner that the triangle described by the points PCL naught, P1 and P3. This triangle is similar to the triangle described by the points Z, PCL min and PCL max. So if the plant pole position alone were to change, then the closed loop pole will move along this blue colored solid straight line as shown here, which passes through the point PCL naught in such a manner that the extremities of this line when connected to the point Z form a triangle which is similar to the triangle formed when the extremities of the point P2 are connected to the point PCL naught, or in other words the triangle PCL naught P1 P3 is similar to the triangle Z PCL min PCL max. So this is the line along which the closed loop pole is going to change its position when we have uncertainty only in the pole location of the plant. Now let us take another case where our plant's gain is not at its nominal value but is at its maximum value. Now when the plant's gain is at its maximum value and its pole location is at its nominal position, we know from the analysis 2 lectures back that our closed loop pole is going to be located at this point PCL max, at the point that is closest to the 0, which I have highlighted with the blue circle. Now suppose the gain is at its maximum value and we allow for uncertainty in the position of the pole of the plant, then we know that the closed loop pole is going to vary along a straight line of this kind, which is going to be parallel to the straight line along which it varied when the plant's gain was at its nominal value. Why is it parallel? It is parallel simply because we still need the extremities of the position of the closed loop pole when we have uncertainty associated with the plant's pole to form a triangle that is similar to the triangle that we have here, namely PCL naught, P1 and P3. Since that similarity still needs to be there, this needs to move along a straight line that describes a triangle similar to the triangle that we have drawn here, namely PCL naught, P1 and P3, and that forces this straight line along which the closed loop pole is going to vary, which I am highlighting now, to be parallel to the straight line along which the closed loop pole will vary when the gain was at its nominal value. What is the magnitude of this straight line? From similar triangles we can see that if ZPCL max, which is this distance here indicated by the blue line, is x by 3 and ZPCL naught is x, then the shorter blue line is going to be 1/3 in length compared to the bigger blue line. So this is going to be the line along which the closed loop pole is going to vary. Now if we take the other case when the gain has assumed its smallest value, namely when the gain of the plant has become 0.3, then we know that our closed loop pole is going to be located at this location, which I am indicating by the blue circle, which is going to be at the point PCL min. Now if we permit for variation in the pole P2, then we know that this closed loop pole should move along a straight line, which I am drawing now, in such a manner that the extremities of this straight line when connected to the point Z forms a triangle that is similar to the triangle that is formed when the extremities of the point P2 are connected to the point PCL naught, or in other words the extremities when connected to the point Z forms a triangle that is once again similar to the triangle PCL naught, P1 and P3. So this in turn therefore implies that this line along which the closed loop pole varies due to the variation in the open loop pole position of the plant is going to be once again parallel to the two other lines along which the closed loop pole varies when the plant's gains are at different values. In the one case the plant gain was assumed to be at its nominal value, in the other case the plant gain was assumed to be at its maximum value. Now continuing this argument further, we can see that for some other value of the gain of the plant which is in between the values 0.3 and 3, our closed loop pole position would be at some other location on this red straight line. It would be at some other point here which I have indicated by this green point, in the absence of uncertainty in the pole position. However, if we now assume that the gain was at this particular value for the plant, but its pole became uncertain and it could wander back and forth between the points s is equal to 0 and s is equal to minus 2, then the corresponding closed loop pole would vary along a straight line that is parallel to the other straight lines that I have sketched in this particular manner, in such a way that it once again describes its extremities once again form a triangle that is with the point z, that is similar to the triangle that the point P2 forms, extremities of the point P2 forms with respect to the point PCL naught. Hence, if we have independent variations in the pole location of the plant and the gain of the plant, it is not difficult to see that in general the closed loop pole will vary within this particular quadrilateral. So for the maximum gain of the plant, the closed loop pole will vary along that boundary when the plant's pole location changes. For the minimum gain of the plant's poles will vary along this edge when the plant's pole location changes, and likewise for the particular pole location, namely at s is equal to minus 2, when the plant's gain changes, the closed loop pole will vary along this particular straight line which I am highlighting here with blue color, and likewise when the plant pole is at s is equal to 0 and its gain changes by a factor of either increases by a factor of 3 or reduces to 30% of its nominal value, the closed loop pole is going to vary along the straight line that I am highlighting now. So these four straight lines form the edges of the region within which the closed loop pole would vary when the plant's gain and pole changes. So for any other intermediate combination of plant's gain and pole location, the closed loop pole will be located somewhere inside this area. So this area is therefore the region within which the closed loop pole would vary when the plant and plant gain and pole locations assume different values within the ranges that have been specified to us. Now our goal as control engineers is to choose the location of the 0 with respect to the point PCL naught, or in other words determine the distance x, so that when the closed loop pole varies within this area, the maximum distance that it can traverse is no more than 0.04 units. So that is what we are supposed to do. So for the sake of geometric calculations, let us name the corners of this square as A max, B max, A min, B min. So one way to approach this problem of restricting the variation of the closed loop pole to within 0.04 units is to determine which of the diagonals of this quadrilateral is the longest, and that longest diagonal would be some constant times this distance x, because this entire figure scales with this distance x, and we should insist that this diagonal should be less than or equal to 0.04 units in order to determine at what position x we have to place the 0z with respect to the point PCL naught. So this is one way in which the problem can be solved. The other way in which this problem can be solved, which is a more approximate but a slightly easier route, is to find the diameter of the circle that circumscribes this quadrilateral, the quadrilateral A min, B min, A max, B max, and insist that the diameter of this circle be less than or equal to 0.04 units, which is the maximum permissible variation in the closed loop pole. However, if you notice this quadrilateral, it is first of all a parallelogram, because the sides A max, B max is parallel to the side A min, B min, and unless a parallelogram is an isosceles parallelogram, it is not possible to exactly circumscribe this parallelogram, and the circle that best encloses this parallelogram is once again slightly difficult to compute. So, if you want an easy way out to quickly estimate the approximate distance at which we have to place the 0 with respect to the point PCL naught, we can instead insist that the entire triangle Z A min B min should be enclosed within a circle. Now, this circle which circumscribes the triangle Z A min B min will be approximately of the same diameter as the circle which encloses the quadrilateral A min, B min, A max, B max, because the points A max and B max are located fairly close to the point Z, but this circle is going to be slightly bigger. So, therefore, our design is going to be slightly conservative. Now, the reason we undertook this step was because there are ready made expressions in trigonometry that will allow us to determine the diameter of the circle that circumscribes the triangle Z A min B min. In particular, if the distance from the point Z to the point PCL naught is x, we noted from our discussions in the previous clip that the point PCL max PCL min, this distance therefore is going to be equal to 0.97 x, and since A min B min is going to be 3 times the length of PCL max PCL min, which is the red curve that I just highlighted now, we would have this distance A min B min to be 3 times 0.97 x, which essentially is going to be equal to 2.91 x. That is the length of the line A min B min. Now, the triangle Z A min B min has an apex angle which I shall call as theta, which is known to us because that angle is essentially going to be the same as the angle that is formed by the extremities of the pole P2 of the plant with the point PCL naught. So, from trigonometry I can obtain the angle theta from the triangle P1 P3 PCL naught, and the same angle is going to be the one that is going to be formed between the points A min, Z and B min. Now, from the sine rule which we learnt in our high school, we know that the distance A min B min divided by sine theta is going to be equal to the diameter of the circle that circumscribes the triangle Z A min B min, circumscribing Z A min B min. Now, here we know that A min B min is of length 2.91 x, and we know the angle theta from trigonometry, and we can show that this angle for the particular locations of the points P1 and P3, that angle is close to 60 degrees. So, 2.91 x divided by sine theta is going to be equal to the diameter of this circle which circumscribes the triangle. So, I shall indicate the diameter by the symbol d here, that is going to be equal to d. And since we want the closed loop pole to not vary by more than 0.04 units, we have to insist that the diameter d of this circle should be less than or equal to 0.04 units. Now, this equation will help us to determine exact distance x of the 0 from the point PCL naught. With that, the first step of our 2 degree of freedom control design gets done. The next step is to determine the orientation of the 0 with respect to the point PCL naught, and to do this we just apply the angle criterion at the point PCL naught, namely the angles obtained by the different open loop poles and zeros of the plant and the controller should add up to minus 180 degrees, and in doing so we ignore the angle contributions from the points P4 and P5 because they are very far away from the origin, and assume that the angle that the point Z bar subtends at the point PCL naught is approximately 90 degrees because the points Z and Z bar are placed very close to the points PCL naught and PCL naught bar, and with this assumption we can obtain the angle of this orientation of the 0 with respect to the point PCL naught. The third step is to determine the positions of the points P4 and P5. For to do that we consider the big picture root locus where we can lump the 2 zeros and the 3 plant poles near the origin with a single effective pole, and use the resulting simplified root locus to determine the gain at which the closed loop pole, one pair of closed loop poles cross over from the left half of the complex plane and to the right half of the complex plane, and determine the locations where P4 and P5 have to be situated such that this gain is less than the maximum gain that the plant can assume. With that we would completely determine the structure of our controller. It would have 2 poles P4 and P5 whose locations we would have determined, it would have 2 zeros whose locations once again we would have determined. Finally we determine the gain of the controller and we would be done with the feedback controller's design. The last step is to determine the structure of the pre-filter, and that is simply given by f of S is equal to Z bar by S plus Z times S plus Z bar, where Z and Z bar are the locations of our controller, feedback controller zeros, and with that our design will complete. I have undertaken this design and I wish to share the results of some simulations that have been performed with this controller design. So this slide shows the plant structure that we have assumed. We see that there is uncertainty associated with the gain of the plant as well as its one of its pole positions. The gain can vary from 0.3 to 3 and the pole P can change from 0 to 2. And associated with this plant we had certain specifications on the desired robustness to these changes in the plant's parameters, and to achieve those specifications the controller structure ends up being something like this. It has 2 zeros whose distance we discussed in this clip, and if we undertake the rest of the design for the feedback controller we can obtain the locations of the points P4 and P5 as well as the gain of the feedback controller. This completes the first 4 steps in the design. The last step is to determine the pre-filter, and the pre-filter is intended essentially to cancel the controller feedback controller zeros and thereby allow the dominant poles of the overall transmission function to be at the points minus 1.5 plus minus 2j. So with this feedback controller the root locus of the feedback system looks as it has been shown here. So the poles of the plant and the zeros of the controller are situated very close to the origin and are not visible in this particular graph. We only have the far away poles of the plant that are visible at the point S is equal to minus 460. In order to view the root locus in the vicinity of the origin we zoom into the area near the origin where we can locate the points P1, P2 and P3 of the plant and the points Z and Z bar, and the root locus appears the way it is shown in this figure. Now when we change the gains of the plant within the limits that have been specified and the pole locations of the plant within the limits that have been specified, we can verify from root locus that the variation of the closed loop pole is actually within 0.04 units. So now that we are done with the design we can now look at the step response of the overall closed loop system. That has been plotted in this graph here. What I have plotted here is a step response of a 1 degree of freedom control system. So we do not have the pre-filter here, we just have a feedback controller which ensures that the nominal positions of the closed loop poles are at minus 1.5 plus minus 2j. However, when the plant's gain changes or when the plant's pole locations changes, the controller cannot restrict the variation of the closed loop pole about its nominal position. As a consequence, what we see here is this huge spread in the transient response of the closed loop system to a step input for different possible values of the gain of the plant and its pole location. In contrast, if one were to plot the step response for the same uncertain plant, but this time with a 2 degree of freedom controller, one can see that for all the different possible combinations of the plant's gain and its pole location, the response, step response of the closed loop system almost exactly sit one on top of another, with practically no perceptible variation between them. This once again underscores the power of a 2 degree of freedom control strategy to achieve robustness or insensitivity to variation in the plant's model. In the previous two clips, we looked at uncertainties associated with only one of the parameters. In one case it was the gain, in another case it was the pole location. In this case we have assumed that both the gain as well as the pole position can change, but despite these changes we are able to design a control system that ensures robustness to variation of both these parameters independently. Now the reason that we have got such a good response in this case was because we restricted the variation of the closed loop pole to just 0.04 units when the plant's pole or gain were to change. If we were to relax this constraint a little bit and if we were to permit the variation in the closed loop pole to be within 0.4 units instead of 0.04 units, we can allow for slightly greater spread in the variation of the transient response of our closed loop system when the plant's parameters change. So when we do that, we see that the spread is slightly higher, but still the performance of the 2 degree of freedom control system is significantly better than the performance of a 1 degree of freedom control system. The benefit of relaxing this variation is that we end up with a controller whose pole is at s is equal to minus 46 instead of at s is equal to minus 460, and also a controller whose gain is much smaller than that of the gain of a controller which has to restrict the variation of the closed loop pole to within just 0.04 units. The pre-filter however has a very similar structure as that of the pre-filter in the previous case. Hence we have seen in this clip that it is possible for us to address the problem of independent variation of two parameters of the plant and design a control system that achieves a specified amount of robustness in the face of independent variation of these two parameters. What we shall do next is look at how we can take up a slightly more challenging problem where we have more than two parameters of the plant that could potentially be varying. In particular, let us consider that one of the other poles of the plant, which was nominally at s is equal to minus 2, also has some uncertainty associated with it. Let us assume in this case that this pole can vary anywhere between the points s is equal to minus 1 and s is equal to minus 10. So let me formally state the problem and briefly sketch the approach that we would adopt in order to solve the problem. The steps however for this case are very similar to the steps that we have adopted for the three examples that we have considered so far, and in particular the first step of the design is very similar to the case that we considered just now in this clip where we had independent variation of the gain and the pole location. So we shall focus only on the first step once again, and I shall briefly say how we can extend the procedure that we adopted in this clip to address the problem where we have uncertainty associated with two poles or perhaps even more poles of the plant. So we shall return to this slide where we state the problem. The plant is very similar in structure to the plant that we have been looking at in all the previous examples, but with the exception that this plant has 3 parameters that are uncertain. The gain k of the plant is uncertain, its nominal value is 1, but it can change between 0.3 and 3. The pole location P1 is uncertain, its nominal value is 1, but it can change between 0 and 2. And the second pole also P2, which is nominally at s is equal to minus 2, is also assumed to be uncertain. So it can vary between s is equal to minus 1 and s is equal to minus 10. So there is uncertainty associated with one pole, another pole, as well as the gain. Now how do we systematically design a 2 degree of freedom control system that achieves the specified amount of robustness in the face of the uncertainties that have been specified for the plant structure? The nominal position of the closed loop pole is still expected to be close to minus 1.5 plus minus 2j. So if we look at the steps in the design, the steps are all exactly similar to the ones that we have been looking at so far. We have to have 2 controller zeros placed near the point PCL naught and PCL naught bar, and for the sake of causality we have to introduce 2 controller poles P4 and P5, and we assume that these poles are located very far away. The first step is in the design is to determine the distance x of the point z from the point PCL naught. The second is to determine the orientation of z with respect to PCL naught, and subsequently if we assume P4 and P5 are coincident, then determine the location of P4 in the interest of stability, and then finally finish the feedback controller design by determining the gain of the feedback controller by using the root locus equation that has been shown here. The last step is to determine the structure of the pre-filter, and that is given by this expression here. So if you have fixed the locations of the feedback controller 0, z and z bar, then the pre-filter structure automatically gets fixed. So once again we shall not undertake the design for this particular case, we shall just focus on the first step, which is to locate the 0 z with respect to the point PCL naught. So we saw that in order to undertake the analysis for the first step in the design, what we need to do is determine the shape of the curve or the area within which the closed loop pole would vary when the plant's parameters change. When the plant's gain alone changed, we noted that the closed loop pole varies along a straight line that passes through the point z. In the second case, when the plant's pole location changed, we noted that the closed loop pole varied along a straight line that is different from the straight line in the first case, but the extremities of this straight line resulted in a triangle that was with respect to the point z that was similar to the triangle that the extremities of the open loop plant pole formed with the point PCL naught. So that allowed us once again to determine the distance at which we had to locate the 0 with respect to the point PCL naught. So likewise in the third case, when both the plant gain as well as its pole position were uncertain, we noticed that the closed loop pole could vary within an area. This time it was not a single curve, it was not a straight line, it was an area within which the closed loop pole could vary. Hence our challenge in this new problem is to just determine the shape of the area within which the closed loop pole would vary when the plant's 2 poles are different in position compared to the nominal values, and when the plant's gain is also different compared to its nominal value of gain. In order to solve this problem, I have drawn 3 different complex planes on the left. The first complex plane indicates the locations of the poles P1, P2 and P3 of the plant, which are assumed in this case to be located at their nominal positions, and we consider only the variation in the gain of the plant. In order to understand how the closed loop pole position changes when the gain of the plant varies, I shall zoom into this region near the point Z and PCL naught and separately draw it here exactly as we had done in the previous examples. So this is the point Z and the closed loop pole position PCL naught is somewhere here. Now we know that when the gain of the plant changes, the closed loop pole varies along this particular straight line to between the points PCL max and PCL min, which are 1/3 of the distance from the point Z to the point PCL naught and 3 times the distance of the point Z to the point PCL naught respectively. So, this is the line along which the closed loop pole varies if you have uncertainty only in the gain of the plant and no uncertainty whatsoever in the either of the pole positions. Now, if you had uncertainty in the pole position P1, we notice that the closed loop pole will vary along a different straight line which we sketched out earlier in this clip. So, these were the limits, it would vary along this straight line within the limits that describe a triangle which is similar to the triangle described by the limits of the point P2 with respect to the point PCL naught. So, that was the second case. Now, if both the gain and the pole position P1 varied, we noticed that it would form a quadrilateral, and from this, and the closed loop pole would be located somewhere within this quadrilateral. So, this was our discussion just a few minutes back. Now, suppose we have the other pole also varying. So, suppose we have the pole P3 also varying as has been stated in this problem. It is nominally located at P3 naught, which is at S is equal to -2, but it can vary from S is equal to -1, at which point it will coincide with the point P2, and S is equal to -10. So, in the third graph here I have indicated with this blue line the range over which the plant pole location can change. Now, the problem of determining the area within which the closed loop pole varies when the second pole of the plant also changes its position is not very different from the cases that we have considered before this. So, for the moment let us assume that the plant gain and the first pole are both at its nominal positions, in which case the closed loop pole would be located at the point PCL naught. If the third pole were to wander about, were to change its position with respect to its nominal value, which is P3 naught, then we know from the analysis that we have performed that when one of the poles of the plant were to change, then the closed loop pole varies in such a manner that the triangle described by the extremities of the closed loop pole positions with respect to the point Z is similar to the triangle described by the extremities of the point P3 naught with respect to the point PCL naught. So, this triangle would be similar to the triangle described by the point PCL when the pole location P3 were to change within the specified limits. Now, this is the line along which the closed loop pole PCL will vary if there was no uncertainty either in the gain of the plant or in the pole location P2 of the plant. Now, suppose we also had uncertainty associated with the gain of the plant. So, if the gain was lesser by a certain amount, so let us say the gain was at its minimum value of 0.3, then the closed loop pole would be located somewhere here when the open loop poles of the plant, both the open loop poles of the plant are located at the nominal positions. However, if the point, once again the pole P3 were to vary between the specified limits, then we would have the closed loop pole varying along this particular straight line in such a manner that it describes another triangle which is similar to the triangle described by the extremities of the point P3 with respect to the point PCL naught. So, for let us say we have now uncertainty associated with the pole location P2 as well. So, for the case when the pole P2 is located at the point S is equal to -2 and the pole P3 is at its nominal position and the gain is at its nominal value, our closed loop pole would be located somewhere here. Now, if we permit for variation in the pole P3 of the plant, then our closed loop pole would vary along a straight line that would describe a triangle that is similar to the triangle described by the extremities of the point P3 with respect to the point PCL naught. So, what we essentially do therefore is we consider the variation of one parameter at a time and determine the curve along which the closed loop pole would vary when this particular parameter varies, and then we subsequently allow for the second parameter to vary and then the third parameter to vary, and finally determine the entire overall region in which the closed loop pole can possibly vary when one or more of these parameters change. Now we determine the maximum variation of the closed loop pole within this region in terms of the distance x between the point z and the point PCL naught, and we insist that this maximum variation has to be within the specified limit, which in this case is 0.04 units, and that will allow us to determine the distance at which the 0 has to be located from the point PCL naught in order to restrict the variation of the closed loop poles due to uncertainties in the plant. In this case we have two poles that are uncertain and the gain that is uncertain, but yet we can systematically determine the location of the 0 of the controller from the point PCL naught that restricts the variation of the closed loop pole to within the specified limit. The exact shape of this curve, however, may be more complicated than the one that we considered in the previous examples, and hence one can even take the help of a computer in order to obtain the area within which the closed loop pole will vary when we have each of these parameters of the plant being uncertain. But with that additional step taken into account, one can in a very straightforward manner undertake the rest of the design, determine the numerical value of x, and subsequently undertake the remaining steps in the design where we determine the angle of the point z with respect to the point PCL naught and hence use it to determine the exact position of z, and then determine the location of the far away poles P4 and P5, and then the gain of the feedback controller, and as a last step the structure of the pre-filter. Since these steps are identical to the ones that we undertook in the first clip where we did 2 degree of freedom control design, I shall not discuss the details of these steps in this clip. So with this we come to the end of our discussion regarding achieving robustness for the overall feedback control system to uncertainties associated with the plant, and the examples that I have considered here reveal to you that this control strategy is quite general and can handle uncertainties of fairly large magnitudes and of different parameters in the plant.